All right, good morning, everyone. My name is Jean-Luc, and I'm presenting our privacy-first platform for data backhaul called Nebula. So Nebula's goal is to enable large deployments of battery-powered devices nearly anywhere in the world. They could be densely scattered throughout an urban area or deployed in a dense forest, or even glued onto millions of packages heading to customers. And each of these sensors really has a primary goal, and that's to upload their data to the cloud where it can be useful to scientists running studies or planners managing a city or commercial companies that deployed the sensors out in the wild. Unfortunately, the right way to perform this data backhaul has remained pretty elusive because you have to deal with varying environments, on and off connectivity, and limited device capabilities. So the options are limited. Some methods aren't scalable, like retrieving data from a sensor manually or configuring each sensor to use whatever networks are around them. Maybe you find a Wi-Fi network in a building or something. They might also be really expensive, requiring their own network of base stations and other networking infrastructure. So if you have to set up your own Wi-Fi routers, for example, that can get very complicated. And finally, seemingly straightforward solutions like cellular radios are really power hungry, and that both limits sensor lifetime and makes the sensors really expensive to deploy. So recently, a different approach is to leverage the presence of third-party devices like a phone or a smartwatch or anything else that's connected to the internet that can mule data to the destination. So the sensor opportunistically passes off data using a low power wireless protocol like Bluetooth, and the mules can then send their collected data to a centralized platform provider that can then route the data to a specific application server at a cost, of course. There has to be some cost to running the system. Importantly, these systems already exist all around us. So Amazon's Sidewalk backhauls data through your Ring doorbell camera and home Wi-Fi connection. Apple's Find My Network uses device owners that are around you to let you know where you left your phone. And exposure notifications use local Bluetooth messages to detect interactions with others who are COVID positive. Unfortunately, in these deployments, the platform provider maintains a centralized view of all backhaul traffic throughout the system, which presents a significant privacy risk. If they're malicious, the provider can track what sensors use which mules to backhaul data at approximately what time, and you can leverage this data to follow mule owners from their jobs back to their homes, through parks, and even to sensitive medical appointments if they decide to do that on a particular day. And the reason for this backhaul privacy issue is that the provider is trying to meet a large set of requirements at the same time. So backhaul should be general purpose, and that's capable of sending arbitrary data, but it should also scale to a large number of sensors and mules. You also want to prevent misuse of network resources, enforce authentication, make sure that you're not losing control of the system. And there should be a way to charge for backhaul use. So the more individual deployments use the system, the more they should pay to maintain it. And all of these goals kind of trade off with privacy. So for a system like Sidewalk, where the provider wants to see traffic to be able to tell it where to go and to block spam and to charge applications accurately, all those come at the cost of metadata privacy. It's not really something that is easily achievable in that system. Alternatively, in a system like Find My, you might want to limit the privacy exposure by only allowing sensors to send key material rather than arbitrary data payloads. But at the same time, we can't really use it for generic sensor data, which really limits its usability. And finally, you could use academic work to leverage work in metadata hiding private communication, which in principle will allow us to have both a general purpose and private backhaul system. But unfortunately, these systems really struggle at scale. So sustained use with millions of sensors and mule platforms is impractical. As a result, the challenge is not really in achieving some of these properties, but in finding a system design that satisfies them all at the same time. And this is what Nebula accomplishes. So To be specific, Nebula is a backhaul system that preserves mule privacy while allowing a provider to charge for network use and incentivize mule participation. We do this by leveraging out-of-band accounting, in which applications buy untraceable tokens from the provider and exchange them for data. In a private setting, Nebula can even limit mule misbehavior by removing the financial incentives and allowing application servers to easily filter spam. And we limit application server misbehavior by allowing mules to submit complaints to the provider on a fixed schedule. Finally, we designed Nebula to scale. So where every one data payload sent to an application is equivalent to one token, a provider can perform accounting for almost 450,000 tokens per second, or 250 million tokens per dollar, which supports millions of mules. So first, I want to briefly go over Nebula's core design, and then I'll talk about misbehavior and show you some evaluation. So in a normal backhaul system, the provider is proxying all the data flow from the mules to the applications, which results in this privacy issue. So that's that purple arrow there with the data flow. In Nebula, we bypass the data flow around the provider entirely. So mules anonymously contact application servers directly, preventing the provider from seeing any data-dependent traffic. As a core design element, we use tokens to track this process. And specifically, we use an instantiation of privacy pass tokens, which have some really interesting properties. They're essentially blind signatures. The two properties that we care about are first, that they are unlinkable. So when tokens are redeemed to a malicious server, like a provider, they can't be linked to the clients that generated them in the first place. What this allows us to do is allow the provider to control access to the network resources without knowing who the token owner was, who actually originally got the token. And second, these privacy pass tokens have a one more token security property, where even if you know many valid tokens, a malicious client can't forge any more. What this means is that the only way to acquire more tokens is to participate in backhaul. And this is critical because if we let mules collect tokens over time, we don't want them to be able to just generate free money. So the way that Nebula works is first we do a pre-purchase phase. So at the beginning of an epoch, this could be every few days or months, an application pre-purchases tokens from the provider, which matches the amount of traffic they expect to receive. Then during the epoch, so during a month, for example, mules send data directly to application servers in exchange for tokens, where you might send a payload and get one token in response. And then at the end of an epoch, mules could bring their collection of tokens, kind of just like in an arcade, to get a reward from the platform provider. They kind of act as a proof of upload and are exchanged for that financial reward. Okay, so that's all well and good, but that basic protocol flow assumes that everything goes perfectly according to plan. In reality, the really interesting situations are those in which the mules and the application servers attempt to misbehave in an effort to gain an advantage. So one problem is delivery misbehavior. So during payload delivery, a mule might think they're really smart and send a random payload to the application, hoping for a free token. And even worse, they might decide that's worth it to spam everyone with random payloads, hoping for more tokens in return. In Nebula, we have the sensors sign payloads so that a simple signature check at the application server can discard invalid incoming uploads. Another interesting case is once the application server has the payload, what incentive is there to actually give a token to the mule? Because the app server paid money for those tokens, it would make a lot of financial sense not to exchange a token. And another related case is what if the application server got a little smarter, instead of sending a real token, just sent a bad or already used token back to the mule. The mule won't really figure out that that's the case until the end of the epoch, at which point the application is really free and clear. So Nebula, we have a fourth end of epoch complaint phase in which mules can submit complaints about specific application servers to the platform provider. Complaints contain a proof of misbehavior, which have a commitment the application server made to exchanging a specific token for a specific payload. I'll go into details about this more a little bit later on. In exchange for this proof of misbehavior, a new token is granted to the mule, and they can redeem that at a later time. And because the tokens are linkable, it doesn't link them to the specific complaint later. Okay, so that was a lot of protocol steps, but to summarize, the provider throughout this process only learns a small amount of information for each epoch. It knows how many tokens were bought by each application. It knows how many payloads of Mule uploaded total throughout the system, but not for who or when they were uploaded. And finally, it receives a set of anonymous complaints every epoch if some application servers begin to misbehave. So if you're interested in more details about this, we have a formal proof sketch for privacy in the paper. I would encourage you to check that out and email me if you have any questions. Okay, so now I want to go into a little bit more detail into how the delivery and complaints actually work in Nebula, because this is the core of the protocol. So uh, when delivering data, first a mule will encounter and authenticate a sensor on the ground, receive an end-to-end encrypted payload, and a sensor-signed payload hash. This is going to be its kind of entry ticket into the system. The mule will take this hash and it'll send it to the relevant application server. The application server is going to check the hash, check the signature on it, and decide whether or not they want to receive the payload. So this is really important because if the payload signature doesn't verify correctly, maybe it's spam, maybe something happened to it, or they've already seen the payload, it's kind of a duplicate, they're not going to respond. So they only respond if they actually want the payload. If they do want the payload, they'll pick an unused token of theirs, and they will sign a commitment to the hash and the token that they're willing to exchange in encrypted form. So this is what that commitment looks like. This is really important because we don't want to give the token to the mule right away because it hasn't sent the data, but we do want to commit to it. So we're going to encrypt it using a key that both the application server and the provider know, which will come in handy later. With the commitment, the mule will then send the actual data payload to the application server. And once the application server checks that the data matches the hash that it originally committed to, it's going to sign a response containing the unencrypted token this time, right? So not the encrypted token of the commitment, but a token that you could actually use to redeem. And the issue is what happens if the application server never sends this token, or the application server sends a signed token that is not valid or has already been used by someone else. Importantly, when the mule redeems the tokens at the end of the epoch, the provider is going to notify the mule of which ones are duplicate and valid, so it doesn't have to track that itself. With the set of invalid tokens, the mule is going to start generating complaints. So at the end of an epoch, the mule is going to send a complaint token and the commitment matching the complaint to the provider. The reason we use a complaint token is to limit the number of complaints that a single mule can make every epoch so that they can't tank the application server's reputation maliciously. So there is some sort of rate limiting. It's going to send the commitment to the platform provider, and the platform provider is going to check the complaint token to make sure that the mule can still complain. It's going to decrypt and verify the delivery token, invalidating it out of the commitment. So this is important that the platform provider has the key to be able to unencrypt that token. The reason we invalidate the token is because we don't want to double count tokens in the system. Either you can redeem it normally through the normal redemption process, or you can complain about the token, but you can't redeem the token for money and complain about it at the same time, right? So if the token's already been used, the complaint doesn't count. If the token was rejected by the platform provider, maybe it was wrong or it was a duplicate token, the mule sends over the signed token if it got it from the application server. What this means is that if the tokens mismatch and the token that it got from the application server is incorrect or maybe used by another payload, we have proof that the server misbehaved, that it chose a knowingly wrong value and signed it and gave it to the mule. If the mule didn't get a token after all, it can't send the signed token. And so what it does is it has the option of sending the original data payload matching the committed hash to the provider. And what the provider will do is if it matches the hash in the commitment, it will forward the data onto the application server. This is really important because it means that there's little incentive to maliciously complain if the mule just has to deliver the data anyway to receive a new token. So instead of going through this whole rigmarole of complaining, which you can only do a limited number of times anyway, you might as well send the data to the application server to begin with. Once either the signed bad token or the data is successfully delivered, the platform provider and the mule will work together to blindly sign a new token. So they will run the privacy pass token signing protocol. And the mule will get this new token, T prime, that it can use to redeem in a future epoch. Now, one note that I want to mention here is that for duplicate tokens, the new token generation is done on a first come, first served basis. So if a duplicate token, if two mules try to submit a duplicate token, then only the first person to complain will get the token. Will get the new token. What that does is it avoids generating more tokens than were actually used in the delivery while incentivizing people to complain. So the faster you complain at the end of the epoch, the more likely you are to get tokens from duplicates. Okay, so following that deep dive into the protocol, I just want to talk a little bit about the evaluation, how we can scale to support millions of mules. So the one question that often comes up with these type of networks is, realistically, how many mules are we likely to see in any given deployment, and how much data could we actually backhaul using them? So to answer these questions, we anonymously sampled Bluetooth emissions in a variety of common locations, such as a park, a campus, or an office, and we measured interaction count and duration, which you can see here to the left. And on the right, we also measured the time it takes to establish a secure encrypted DTLS tunnel between a sensor and a mule and perform data transfer. And the fun thing is that we can really put all this information together. So in a park, which is that orange cluster, we see that we can expect a mule every few minutes for maybe 5 to 10 seconds. And on the right, we can see how much data we can transfer in 5 to 10 seconds, which is approximately 2 to 16 kilobytes. So for most sensing applications, this is more than enough data to be transmitted, especially if a mule is coming around every few minutes or so. Now, that was just one example, but if you want to apply what Nebula can do to maybe a different deployment scenario, we have a bunch of analytical energy and memory models in the paper that I'd encourage you to take a look at. Finally, we ask if Nebula can scale at the provider, which remains really the one centralized component of the system. So to test this, we implemented a high throughput database to check each token signature when it's redeemed and to detect any duplicate submissions. So with a single 128 core server, we can perform this process for 445,000 tokens per second, which is fast enough for every person in the US to redeem tokens each month, perhaps using a Nebula-enabled cell phone. And it's also incredibly cost efficient. We can process over 240 million tokens for a single dollar. Okay, that's pretty much it. So to wrap up, Nebula is a privacy-first architecture to enable nearly anything to send data to the cloud. If you were at the conference, you're welcome to come see us at our poster, but otherwise, feel free to send me an email, and I look forward to your questions. Thanks.